Okay, guys, welcome back. Hello, hello. I hope that Friday break was really relaxing. We are on section 16.2 now. We have jumped into 16. We're on section 16.2. I talked about line integrals on Wednesday, and I did a couple line integrals. I'm not going to keep doing line integrals as in the sense of 16.1, because people already asked me, what do these line integrals mean? I jump into 16.2 because we do line integrals so we can do work, circulation, and flux. And so I'm giving this intro to 16.2 because there is a ton of stuff in 16.2. It's not longer than any other section of the book, but there are a few new concepts that you really got to sit down and spend time with. They're not just computational concepts, right? So the subject of 16.2 is vector fields, which itself could be a whole subsection. Work, circulation, and flux. And we will realize that so first we're going to talk about vector fields, which is a new construction, although you have some intuition for this construction. And then we're going to talk about three new ideas: work, circulation, and flux, which are all arise as an integral. In particular, they all arise as a line integral. So that's why I'm not dwelling on 16.1, where it's a bunch of computational things. The reason for 16.1 is to get to these types of line integrals, which are ubiquitous in physical sciences, in mathematics, chemistry, biological sciences. They come up a lot, okay? And so I want to teach you how to compute them, why we need to compute them. But before I do that, I have to talk about a vector field, okay? So a vector field is a map from Rn to Rn. There you go. Okay. We associate to every point in a space, and we usually really want, n greater than or equal to 2. We associate to every point in a space a vector. We will focus on n equals 2 and 3. 2 dimensions and 3 dimensions, okay? So what is a vector field? Here's an example. Let's consider n equals 2. So we have an x, y coordinate system, okay? What is a vector field? You imagine a grid of points. Maybe this is 1, 1. This is 2, 1. 3, 1. 4, 1. And let's keep going. 2, da-dee-dee-dee-dee-dee-doo. 3. And we can go along the axes. So let's imagine gridding our points everywhere. And then at each point, I associate a vector. Okay? So at this point, say where I'm standing, there's a vector. At this point, there's another vector. At this point, there's another vector. At this point, there's another vector. So at every point, there's a vector. So just draw this. This is a vector field. Or this is a representation of a vector field. This is how we visualize a vector field. The way we think about it is that we have a vector field I'm going to call V vector is the vector field. It's a function of x, y, and z. And it has components. Now, in your book, they use m, n, and p for components. Okay? So actually, let me not write this here. I should write this on the next board. Give ourselves some space right underneath this. We have v vector, which is a function of x, y, and z. It has components m of x, y, and z, I hat, plus n of x, y, and z, j hat, plus, if we're in 3 dimensions, this would be p of x, y, and z, k hat. I am using your book's notation, okay? However, we are only in 2 dimensions, so it's really a vector field as a function of x and y, and it only has 2 components, I hat and j hat. And now you see what I mean by it's a map from Rn to Rn. That is to say, it takes n real numbers. In this example, it's just 2. It's x and y. And it spits out n real numbers, 1 here and 1 there. So this is 3. Okay, this is in 3D. Maybe I'll write it in 2D. In 2D, we would write v vector of x and y equals m of x and y I hat plus n of x and y j hat. I'm using m and p because that's the notation your book uses. Okay? M is the x component of a vector, n is the y component of a vector, and p is the z component of a vector. The way we visualize it is we go to each point in this space and put the vector, the tail of the vector at that point, and then draw a vector at that point that goes from the tail in the direction m, n, and p. Okay? Now, this is a little comment I want to make. What are examples of vector fields that you may have an intuition for? Well, the classic one is wind. Okay? If you look at a weather map and you plot the wind vectors there, at every point on the map, there is a vector of the wind. Okay? What are the units of the map? What are the units that get you around the map? What are the dimensions of the space? It's a 2-dimensional space because we're doing horizontal, x and y. And you go meters in one direction and meters in the other direction. So to get you around the space, the x and the y are given by lengths. The vector, which is a velocity vector, is in meters per second, for example, because it's a velocity. So these vectors do not have the same units as the units of the space you're living in. Okay? So they're a map from this space to some other space. Okay? It happens to be that this space is 3-dimensional. In particular, this has the same number of dimensions, okay? But they're a different space. And I say that because I always want you guys to think about the units of the thing you're writing. Think about the units. Think about the units. Think about the units. Okay? It helps solve problems all the time. And when you get confused in a physics or chemistry class, if you make sure you've done your units right, you're going to increase your probability of getting the right answer. Okay, now I just want to remind you that there was another vector sitting here, which was the position vector. Remember r, which was the position vector? And we did it for like curves in this space, like r of t. Okay? What was the position vector? It's very different. The position vector has units of length, right? Because it tells you how to go from the origin to a given point in this space. And ideally, I would have a different color of chalk here, but let me do it with sort of a broad chalk. There's the position vector from this point to here. Okay, that's r. That's the position. So this bold thing is r vector. Okay? So now I want you to distinguish between a vector field, which is 3 numbers at every point in space, the 3 components of a vector at every point in space, and the vector, which is the position vector from the origin to a given point. Okay? Often this vector field, I will write v of r. Or you will see this as v of x vector, where this is simply a shorthand for x I hat plus y j hat, or this is a shorthand for x I hat plus y j hat. Okay? These are notational. These are commonly seen in different textbooks. If you go to England, they write it one way. You go to France, they write it another way. In the United States, they write a third way. In Canada, they write it a fourth. Okay? And you guys are all international engineers to be. international engineers to be. So you should know the different notations you may encounter. Okay? So this is what a vector field is. What we really care about in calculus is that these functions are differentiable. Right? You can have some crazy vector field, right? You can have a crazy vector field where you have some vector over here and like immediately beside it, it goes like that. That's just a crazy vector field, right? That's not differentiable. But that's not, we got to be able to do calculus on things. And so we realize, hey, there's 3 functions. I better have, everybody is, I can take derivatives. I can evaluate these functions pretty much everywhere in the space. Those kinds of conditions are typical of the vector fields we consider, okay? Now, what are the vector fields that we encounter? Well, I said one was the wind vector, so e.g., one is a wind vector field. And I really suggest you can take a look at Earth, what is it? Null.earth school. Did I show you this? .net. Anybody seen this? So those of you who are bored at the moment and don't want to hear my lecture, go on your phones and find this website, okay? This is one of the coolest little websites you'll ever come. I think it's cool. I mean, I'm an old guy. It's got a picture of the globe, and you got all sorts of vectors, which are the current wind field on the globe right now, the whole Earth. And then you can color code it with the current temperature at those locations, and you can choose what height you want to see. So whenever you're bored in class, in my class, you should be doing this, because you should be looking at vector fields, okay? So if you're bored in my class and you want to go look at this, you can go do that right now. Okay, stop texting your significant others. They won't help you get through calculus. Unless they really like you. Where else? Okay, so that null.earthschool.net, I think, it's just one that I stumbled upon. Wind on the Earth right now. Google that or whatever that is. What else? That's a wind vector field. Well, you have, even in this room, you're experiencing a vector field every moment of time, right? Which is the gravitational force, the force of gravity. That's a vector field you have a lot of intuition about, okay? I want to point out to you that you are experiencing another vector field because I'm gabbing at you, okay? And by me talking to you, you're experiencing an oscillating vector field, a vector field that's not constant in time. It's a vector field of the air as it sends a wave through it, and the air is compressing and expanding and compressing and expanding and compressing and expanding. So it looks like a little wave, and it changes in time. And so that air is compressing and expanding all the time. So the compression of a sound wave, and those of you guys who've taken E&M, and probably haven't taken E&M yet, electricity and magnetism, a lot of the structures we're developing are to help you solve problems in E&M. Okay, the electromagnetic field, the EM field of light. Okay, and in fact, this is 2 vector fields. This is 2 vector fields. The electromagnetic field is the electrical field and the magnetic field. And so if the light's coming toward you, the electrical field of that light is oscillating in the transverse direction, and the magnetic field all perpendicular to that. And that might be circularly polarized or right polarized, depending on the polarization of the light coming toward us. This is just generally randomly polarized right now. So the electromagnetic field of light. So vector fields, whereas these are vector fields that are just snapshots in space, they also change in time, and that makes interesting dynamics. So you can imagine that these would depend on time also, right? And they do. The gravity of the Earth depends on time. The gravity that we experience here depends on our distance from the sun or our distance from the Earth. Okay, so what? You're like, okay, there's some very general introduction to vector fields. I would like to draw a few vector fields. I want to teach you how to think about vector fields, so I want to draw a few for you, okay? So let's start with the easiest one. The easiest one is the constant. Okay? And then the one that you have experience, the constant vector field that you basically have experience with is gravity. Okay? So, e.g., the force of gravity equals negative mg k hat, where m is the mass of the person feeling it. Okay? So if I were to draw a 3-dimensional space which I'm not going to do. I'll just do 2 dimensions. This is the x direction, and this is the z direction. Okay? I were to draw this vector field, I would go to each point in this space and evaluate this function, right? This is a vector field f, which could depend on x, y, and z. Okay? And if I were to draw this vector field, it would be constant. Now, those of you guys who've taken a physics class realize that I'm sort of lying to you already, right? So I'm going to every point in space and saying it's constant. Now, is this absolutely true? Well, of course, it's not absolutely true, right? What happened? What is the vector field we experience, mgk hat, right? Well, what we're feeling is the vector field of the Earth's gravity close to the surface of the Earth. So we can think of this as the first term in a Taylor series expansion. Ow, the pain. This is the first term in the Taylor series expansion of the gravity of the Earth evaluated at our point. Because the first term in the Taylor series expansion is f, some function at a point is constant plus linear plus quadratic plus cubic. So this is the constant term. Okay? And of course, if you get high enough up, this changes. But let's just talk about being within the atmosphere, and gravity is pretty much constant within the lower atmosphere. Okay? So it's a constant vector field pointing down. And of course, your vector field for the force of gravity is different than my vector field, because I'm a much bigger m than you are. Right? Almost unconditionally in this class. Okay, you guys are all nice, light, young people. Okay, so there's the constant. Okay, that's an interesting one. So that's constant. Now you got one example under your belt. It's like building up functions, right? You had to start with a constant. Then you have to do a linear. Okay, so let's consider a linear function. And by the way, when it comes to plotting, I'm going to pretty much stay with 2-dimensional vector fields, because it's bad enough for me to try to do a helix. You guys were laughing at me with the helix, right? Let me try a 3D vector field. It's going to be a mess. MATLAB does a great job of this. And Octave. Does everybody know about Octave? Octave is a free version of MATLAB. It's a GNU product. It's almost exactly like MATLAB. So if you can learn Octave, you will save yourselves a lot of trouble. Okay, you can download it for a whole bunch of different operating systems. Octave. Okay? And you just learn a little bit of syntax, and you can plot these vector fields. And so why do you do this, right? Gaining a little bit of intuition makes your analytic problems a lot easier to handle. So if you can plot, I couldn't plot vector fields when I was your age, because I didn't have a cool plotting program, right? And so we had to do it by hand with a goat. It's just like, it was, I don't want to sound like some crotchety old man, but it's good that you have these intuitions now. You can push yourselves that much farther, okay? So learn a little syntax. Go jump into Octave and just, grab some code from online. Then you learn, that's how I learned how to code. I learned how to code not by taking any coding class. I learned how to code. I saw somebody else's code. I saw what the code was. I saw what the output was. I put it together. I'm like, okay, that's how you do it. And I made a ton of mistakes, and then I made a code that worked. And I wrote a PhD on a code. Okay? Never took a class on a code. That's the way you do it. So go like this. Go to Octave. Take some source code. Steal it from online. Play with it a little bit. Make something of it, okay? It's all free stuff anyway, right? Most of these libraries are free. Octave. I had a lot of coffee today. I'm going in a lot of different directions. I apologize. It's like, hold on, everybody. Okay, that was the constant vector field. How about a linear vector field? A linear vector field, okay? So let me do a simple linear vector field. Let me do u vector equals a linear function of x and y. So by the way, here's an arbitrary complicated linear function of x and y. Ax plus by I hat for some constants a and b plus abc, and I think d comes next. Here's an arbitrarily complicated linear function, x and y, okay? By the way, those of you who take linear algebra should think about A, B, C, D in a matrix and think about how that fits into a matrix, and maybe this would be related to matrices, and vector fields and matrices are related to each other. So much to tell you, so little time. This is too complicated to analyze just like this. It's 4 parameters. All right, so even a linear vector field is just too complicated for me to just write down just like that. So let's do a couple of cases, okay? So how about I do the simple case A equals, no, let me say B, C, D equals 0. B and C and D are equal to 0. So case B equals C equals D equals 0, A equals 1. Okay? Just this is how we gain intuition about the world. So U of x and y is equal to x I hat plus 0 j hat. So first thing you see, this is a vector field all pointing in the x direction. So this is a vector field that's always pointing in the x direction. That makes it kind of easy. Okay. It's always pointing in the x direction. The I hat direction. 2 doesn't depend on y. What that means is that if it doesn't depend on y, if I can plot it at some fixed value of y, I just copy it as I go up or down, and it's going to look the same. Okay? Notice that its magnitude, so this is important. Look at the magnitude of the vector field. The magnitude of a vector field is equal to its first component squared plus its second component squared square root. Its magnitude is equal to x, or the absolute value of x. Which means that as you get farther and farther in x, it's getting bigger and bigger and bigger. Okay? When I look at a function, these are sort of the things that I ask myself. Where is it pointing? Does it depend on, does it have an invariance? This is called an invariance. Right? And how does it grow or decay as I move away from the origin? Okay? So when you look at a vector field, ask yourself these kinds of questions, and they'll help you visualize it. Okay? So it says, so clearly, by the way, at x equals 0, this vector field is the 0 vector field. And it switches direction for negative x and positive x. So if I draw this vector like this, it goes like this. And it's invariant in y. Something like this is what's going on here. So all these vectors should be the same length. I mean, I'm being approximate. I'm sketching. But it gives me an intuition for what's going on with this vector field. And in the, for an x negative, it's doing the same thing, but pointing in the opposite direction. Invariant in y, getting larger. Well, that's a little ridiculous, but getting larger as you get farther away from x equals 0. So that's a simple vector field. Okay? Okay, what about, so I set A equals 1. This is an interesting little vector field. I don't know really what to call it. It's sort of a stretchy vector field, right? If you imagine this as a set, like maybe some forces on a membrane, you're stretching it out very far in this direction, okay? By the way, if you have the negative sign, it would be restorative, right? It would be restorative. And in fact, it would be actually related to the force of a spring. This is related to the restoring force given to you by a spring, okay? So how about case A equals C equals D equals 0, B equals 1. So here's a different case, B equals 1. In that case, you've got U of x and y equals y I hat plus 0 j hat. So what do I ask myself? I said, notice that always pointing in I hat direction. So it's parallel. It's pointing only in the I hat direction. So it's going to just be pointing left and right also. Okay? But now this time, case 2, it doesn't depend on x. It doesn't depend on x. It doesn't depend on your horizontal coordinate. It's always pointing in the horizontal direction, but it doesn't depend on where you are in the horizontal direction. Okay? And the magnitude, that's always a nice thing to plot. The magnitude of u is equal to absolute value of y. So it gets bigger as you get farther away from y equals 0. So what does this thing look like? Okay? At y equals 0, it's the 0 vector field now. So along this axis right here, It's the zero vector field. As you get a little bigger in y, what happens? Well, as your y is positive, u is positive. So at y equals 1, u equals 1, I hat. So it's going like this. And it doesn't depend on x, so whatever vector I put here, I basically have to make a copy there, and I keep copying it, okay? I've made these a little large, I'm sorry. As I get bigger, these vectors get bigger, and like this, and like this. And if I go to negative values of y, they get bigger, but in the opposite direction, okay? So this is a, by the way, in fluid dynamics, this has a name. This is called a shear flow. This is a shear. If you imagine just putting the ground right over here, and the wind was blowing overhead, right? Well, the wind sort of has to stick to the ground because of viscosity, because of just the dynamics of air. It actually ends up sticking at the ground. And then as you go away from the ground, it's a linear function of height. Okay? It's going to be a linear function of height, at least for a small value, for small values of height. Okay? Well, this is a shear flow. This is true about this. This is a wind shear, vertical wind shear. This is the stuff that happens in the atmosphere, happens in oceans, near boundaries, everywhere. Okay? So that's another simple one. Okay. These are basic vector fields, and you may roll your eyes again about this, but how have I built them up? I started with constant. I go linear. You could go quadratic. You could go cubic, and I'm essentially building up the Taylor series expansion of vector fields, of vector functions, right? So you could think about Taylor series expansions, because in your book they'll start giving you these arbitrarily complicated vector fields. Right? Some wacky function, hyperbolic tangent, cosine of all this stuff. But in the end, you go look at a vector field, and you go look near a point. And you say, what's going on with the vector field near this point? Like the wind, right? Near a point, the wind is blowing past me, and it might be kind of shearing around me a little bit. It may be lifting up a little bit. But those are like the first few conceptual terms in a Taylor series expansion. Okay? So it's evaluating the vector field, evaluating its derivatives, et cetera, et cetera, et cetera. Okay. So these are some basic vector fields. At this stage in the class, I go a little rogue. So I want to talk about three vector fields, three basic vector fields. Okay? I'm going to talk about these three basic vector fields because they're extremely tightly related to a problem you're going to do in linear algebra in 22A. Okay? So let me do these three basic vector fields. There are three linear vector fields. So one, the radially outward vector field. Two, the rotation, the solid body rotation. And then three, is going to be the x point or the pinch. I'm going to call it a capital X point, or pinch or squeeze. Yeah, let's just call it the X point flow. Okay? We'll just call it the X point flow. By the way, we are going to learn about two vector operations coming forward. I have to foreshadow a little bit, okay? So we're going to learn about two vector operations. We're going to learn about the notion of a divergence of a vector field, and we're going to study what the curl of the vector field is. These, if you can understand these three basic vector fields, right? These three basic vector fields will have the property that locally, one will be all divergence, no curl, one will be all curl, no divergence, and one will have no divergence or no curl. So these are the basic local vector fields that will explain. If you can understand what they're doing, look at what they're doing, then you will understand what it means to take the divergence, and you will understand what it means to take the curl. That's why I do these vector fields. Okay. So, actually, I'm going to stay over here. I apologize. Let me stay over here. The radially outward vector field. I want us to make these vector fields. I want to think of them as velocity fields. I want to think fluid dynamics. Okay? So I want you to think that you're stirring a cup, okay, or doing something with a cup. Okay? and we're going to flow the fluid. And we're just going to look at a two-dimensional surface of the fluid and look at the vector field just at the surface of the fluid. The radially outward vector field is u vector of x and y is equal to alpha times xi hat plus alpha times yj hat. This is the radially outward vector field. If u is a velocity field, it's in meters per second, and x and y is measured in meters, therefore alpha must be measured in reciprocal seconds. Okay? Keep that in mind all the time when you think about these problems. The solid body rotation vector field is going to be u of x and y is equal to, alpha x j hat plus negative alpha y I hat. Yeah. Negative alpha y I hat plus alpha x j hat. Okay. Let me start with these two vector fields, and I'll get to the x point in a second. These are even more fundamental. Okay. So notice there's no symmetry in this problem. It depends both on x and y. This one also depends both on x and y. Okay? But what is the magnitude of u in this problem? The magnitude of u. The magnitude of u is equal to this squared plus this squared square root, which is equal to alpha times the square root of x squared plus y squared. And when you do that, you see there is symmetry. I like the scratching of the chin there. At least somebody saw that symmetry. X squared plus y squared, square root, is the distance from the point where you're evaluating the vector field to the origin. So this vector field is actually a linear its magnitude is a linear function of distance from the origin. So it gets really, really, really small when you get close in, and really, really, really large when you get far out. Okay? That's this vector field. What about this one here? The magnitude of u for this vector field is equal to alpha the square root of x squared plus y squared, which might as well call it r, which is r is the radial coordinate, right? Is a polar coordinate for the square root of x squared plus y squared. That's cool. That's interesting. Now, what else? Well, I'm going to tell you that this is going to be super easy to plot. We're going to super easy plot this one in a second. If I can super easy plot this one, I'm going to say it's super easy to plot that one. Why? Notice, vector field 1 and vector field 2, I call them both u, and you might be a little mad at me for doing that. They're two different vector fields, right? This is example 1 and example 2. But let's take the dot product of these vector fields. Okay? Consider the dot product of those two vector fields. And that tells you something. What does the dot product tell you? Well, I always like to think of it as the shadow of one vector on the other. Okay? But consider alpha x I hat plus alpha y j hat dotted into negative alpha y I hat plus alpha x j hat. The dot product basically says multiply, because we have an orthonormal basis, I hat and j hat constitute an orthogonal normal, that means they're a unit vector, basis. When you take the dot product, it's first coefficient times first coefficient plus second coefficient times second coefficient. And this is clearly negative alpha squared xy, first coefficients, plus alpha squared yx, second coefficients, which is equal to 0. It's not just 0 at any point. It's 0 for all values of x and y, which means these two vector fields are perpendicular. Therefore, these two vector fields, VF I'll use for vector fields, are perpendicular for all x and y. At every point in space, they're perpendicular to one another. Okay? So I know that they have the same length as a function of distance from the origin. I know that they're perpendicular to one another, so it's really easy now. If I can plot one, the other one just pops out of the whole thing. And I've given them names already, so it's probably pretty obvious what they're going to be. Okay? But let's plot them out. And if you plot them out, so plot u vector equals alpha x I hat plus y j hat. Notice I factored the alpha out, and I'm going to use alpha greater than 0. You'll see where the difference is. Okay? Well, how do you do this? How do you do this? We know, I'm going to just sketch in these circles here. We know that the vector field has constant magnitude on each of these circles, that the length is the same on each of these circles. Okay? And the easiest thing to do would be to evaluate the vector field, say, at this point right here. Just choose a point. When in doubt, evaluate. This is the point x equals, say, 1, y equals 0. So u is equal to alpha. So u is equal to alpha I hat. So it's pointing out in this direction, alpha I hat. And then here would be, say, like 2 alpha I hat. And here would be 3 alpha I hat. And over here would have the same length, but it would be pointing in the j hat direction. You get that, it's going out. And if you go, say, at 45 degrees, pi by 4, on this circle, you'll realize that this thing is pointing radially outward in this direction. And then you'll realize that it's pointing radially outward in this direction. And so I've often called this an explosion, but one of my students pointed out once that it's not really an explosion, because this is a vector field which is increasing, whose magnitude is increasing you get farther away, and the explosion, the magnitude decreases, right? So, and then decreases. So it's kind of the opposite of an explosion. This is the radially outward pointing vector field, okay? Now, for those physics folks in the audience, so this is what you should do is draw these kind of radially outward pointing vectors, getting bigger and bigger and bigger as you get farther away. If I were to take u vector and divide it by the magnitude of u, we know that this is a unit vector by definition, and this is going to be equal to x divided by the square root of x squared plus y squared I hat plus y divided by the square root of x squared plus y squared j hat. And this, my students, is the direction of that vector field, right? U, the vector divided by its magnitude, just is purely a directional thing. Now you look at it and you're like, ugh, what is this? What is this thing? Well, it's screaming polar at you again. I hope it's screaming the polar coordinates. So here is the Cartesian representation of this vector field. But what is the polar representation? Well, the polar representation is, I'm going to still use a Cartesian basis, I hat and j hat, but now I'm going to recognize that x is r cos theta and y is r sine theta, and the r's are going to cancel out. So this is going to be cos theta I hat plus sine theta j hat. And so the direction vector is cos theta times I hat plus sine theta j hat. And now it might be a little easier to see how to plot it, because what you do here, and I'm only going to do one quadrant over here, when theta equals 0, sine theta is 0, cos theta is 1. So when theta equals 0, you're pointing in this direction. When theta equals pi over 4, cos theta is 1 over the square root of 2. Sine theta is 1 over the square root of 2. You're pointing equally in either direction. And then you go, and I'm just doing it over one circle, and then you're pointing up there. And then you can convince yourself that depending on the angle here, theta, between the x-axis and the point of evaluation, that'll determine the angle of the vector. Okay? There's a lot there. I just told you a lot of stuff in those 3 sentences. Okay? So you need to practice this kind of stuff to absorb it all. I know it's a lot, okay? But we do have to think, you do have to think this way if you really want to understand these vector fields. Okay? That means you got to say, sometimes I got to throw a different coordinate system in there. Sometimes I have to look at that function a little differently. I have to represent it in polar. It might look nicer in polar. Okay? And when do you do that and when do you don't? When do you don't? When do you do that? You do that whenever you come up to a block. You're sort of blocked with making any progress. You start throwing things at it, new coordinates. Maybe that'll help, okay? Part of what I'm doing here is trying to give you a repertoire, kind of a basic toolbox of vector fields. Okay. Oops, did I lose the... What's the matter? Am I losing my, am I talking? Did I lose the microphone? Okay, I'm back. But you guys can always hear me anyway, right? Can you hear me online? I got the deep voice when I talk into the mic. Thanks. Okay. I'm still getting used to this whole microphone business. That's what this vector field is radially pointing outward in all directions. Okay. Well, like I said, if I know one vector field, I know the other one. Okay. What about the second vector field? Let's plot u vector, this different one, which is equal to negative alpha y I hat plus alpha x j hat. What we said was, yeah, you know that the magnitude of u is alpha times r, where r is the square root of x squared plus y squared. We already did that. And u divided by the magnitude of u is now equal to negative, oh, sorry, this is a negative, right? This is a negative over here. Negative y over the square root of x squared plus y squared, I hat, plus x over the square root of x squared plus y squared, j hat. And again, y is r sine theta and x is r cos theta. So this is different now. This is negative sine theta I hat plus cos theta j hat. And notice what's happened here. The sine theta and the cos theta have reversed roles with a negative sign. And that's always an indication of perpendicularity. Okay? So if you were to plot this vector field, we already said it's perpendicular. At every point, so let's take along a constant circle. We know everything is sort of invariant along circles. And the original vector field was pointing outward for alpha is positive. This one is perpendicular. It's pointing along the circle. It's pointing along the circle. And if you go, this is tangent everywhere to the circle. And it has the same length as the other vector field. And by the way, this is called a vortex. This is a vortex. This is the basic vortex. I come from a fluid dynamics background, so I like to always make reference to flows, right? Because I can see them. I can stir my coffee cup, and I see that vortex. Okay? This is also the way a record spins, or a CD, or any sort of rigid object that's spinning, because its velocity is a linear function of distance away from the axis of rotation. Right? This point out here is going way, way faster, because it's got to go a longer distance but get around in the same time. Okay? So that's the rotational vector field. That's the solid body rotation vector field. For those of you guys who are taking linear algebra, that vector field is related to matrices, diagonal matrices of trace 1. This vector field is related to antisymmetric matrices. And then this last vector field will be related to symmetric matrices of trace-free symmetric matrices. So put that in your little box in your head. You'll take 22A next quarter, and you'll be like, oh, cool. Maybe. Or you'll be like, I forgot the box. I forgot the key to the box in my head. So the last vector field, the third vector field I wanted to tell you about, which is related to symmetric trace-free matrices. And I will never test you on such an idea. Is, e.g., the x point, okay? And this is u vector is equal to alpha x I hat minus alpha y j hat. So it's a little more complicated. Okay, it's a little more complicated. So notice that the magnitude of u is still equal to alpha times the square root of x squared plus y squared, which is alpha r. So it still has the same property. It gets bigger linearly with distance from the origin. Okay? But now, u, this direction vector, which is u vector divided by the magnitude of u, is equal to, well, the alphas will cancel out. If you do this right, this is going to be cos theta I hat minus sine theta j hat. Okay? And if you notice, This vector is not perpendicular to that one because it's sine cos with a negative and sine cos again with a negative. So they're not perpendicular. Maybe at a couple points they're perpendicular, but in general they're not perpendicular. It's not perpendicular to that one. It's cos cos minus sine sine. So yeah, cos squared minus sine squared. It's not perpendicular to that one. It's not perpendicular, right? Just not. So you got to just plot this thing out. X and y. And what happens here? Well, we know that its magnitude is constant on circles. Okay? Now let's see what direction it takes along this circle. Okay? So let's set x equals 1, y equals 0. It's pointed in the I hat direction. So it's pointed out over here. Okay? X equals 1, y equals 0. Alpha, well, let's just say alpha is positive. It's just the constant that I need to make it have the right dimensions. Let's go to y equals 1, x equals 0. X, that's in the negative j hat direction. So it's going to go like this. Okay? And if you've got 45 degrees, you're going to get different behavior, et cetera, et cetera. Let me show you what these things look like. Okay? You can go through this whole thing. I'm just kind of short-circuiting it. These are getting longer as you get farther out. And you'll see now, I hope you'll see in a second why this is an x point. If you were to just put some water in like in a little, maybe in a plus signed kind of tube, cross tube, and you suck the water out one side, it sucks in the other side. And this is the x point over here. Okay, this is where they cross. Okay, and there's hyperbolas in here. You can see that these things are really this correspond to flow along these hyperbolas. Okay, so that's why it doesn't come out as nice and neat. So this is along circles, that's along rays, and this is along hyperbolas. These are the basic sort of elements of vector fields. Locally, if you go to any complicated vector field and you go just say, I want to study you like right around here. Okay? Well, near any point, there's a Taylor series expansion. The first term of the Taylor series expansion is the constant. The second term are the linear terms. And they break up into three things. A bit of that, a bit of that, and a bit of this, except this could be rotated, right? There's no reason why this axis had to be along the x and y axis. I could have rotated it. It's a little more complicated than this. And then you go to the quadratic and the cubic and the quartic, et cetera. Or you just can take a look at the whole vector field and it looks like a total mess. Okay? Because generally vector fields can be a total mess. But you want to understand them locally. When we do calculus on things, we're understanding things locally. Okay? So those are the vector fields I wanted to talk about today. And I actually got through them in one day. I'm very happy with that. So what's next on the agenda, on the menu? We're going to start studying curves going through space where there's a vector field sitting there. So the curve is like your trajectory through space, right? In x, y, z space. And there'll be a vector field. Usually that's a force field, or maybe it's a wind field, like you're biking through the wind, okay? And you want to understand what is the interaction of that vector field with that curve? Okay? And that's where we're going to define work, circulation, and flux. So I ask you to read section 16.2 before Wednesday, okay? And try to get a little ahead of things. We will do 16.2 this week. It'll be Wednesday and Friday of this week. So it's a much more drawn out section. And then we'll get into section 16.3 next week. Okay? So I hope that was a little edifying, and have a good one.